Hello, this video is introducing a physics project about circular dichroism. First of all, our purpose of this experiment is study circular polarization through design and construct CD spectrometer, and use this spectrometer to measure some physical feature of chiral molecules.
Circular dichroism, or CD, is an absorption spectroscopy method involving circularly polarized light and the differential absorption of left-handed and right-handed light. CD investigates structural aspects of optically active chiral media, and it is mostly used to study biological molecules involving their structures and interactions with other molecules. Left-handed and right-handed circularly polarized light represent two spin angular momentum states of a photon. The handedness of the circularly polarized light describes the direction of rotation of the E field vector as seen by the observer. This is the common convention and the convention used throughout our experiment. If the spin vector and momentum are in the same direction, then it is right-handed. A standard clock having its spin vector defined by the rotation of its hand and is tossed with its face forward is left-handed. CD is exhibited in the absorption bands of optically active chiral molecules. Optically active chiral molecules will preferentially absorb one direction of the circularly polarized light. The difference in absorption of the light and right circularly polarized light is what we are measuring. Are molecules that cannot be superposed on their mirror images. All biological systems are chiral. As the image above describes, the mirror image of our hands cannot be superposed. The word chirality is derived from a Greek word meaning hand. Other examples that come to mind are examples Professor Zhao mentioned in class, such as shells and compounds of oranges and lemons. These groups are ionometers, meaning the mirror image. In our experiment, we used L-cysteine, which is symmetrical with D-cysteine. A study published in the National Library of Medicine and National Center for Biotechnology Information relays L-cysteine is a non-essential amino acid and thus is one of the building blocks required for the synthesis of proteins. We are using L-cysteine because it CD plots across the visible light spectrum. Chiral structures have same but different chemical and physical properties, different properties in reaction with other chiral molecules, and opposite properties in optical activities. Ionometers can be distinguished by CD spectroscopy because different ionometers interact differently with polarized light. We expect that they will have a mirrored CD plot.
The opposite optical activities mainly refer to absorbance of a pair of circular polarized light. The circular polarized light is a kind of light that the electric field vector of the wave indicates a point on a helix oriented along the direction of propagation. The phase difference is the key factor of circular polarized light. When a linear polarized light passes through a quarter wave plate, and the direction of linear polarization is not parallel with fast axis or slow axis, the electric field vector will have a component in each of the directions of two axes. Then the two components will have a phase difference of a quarter wavelength. As the components combine, the light rotates. If the components in each direction are equal, that is, the linear polarization direction is at an angle of 45 degrees respect to one axis, the light will rotate as a perfect circular. Also, CD is an extremely important technique in biochemical analysis. UV is used to study protein structures. Near-infrared is used to study transition metals. And the visible light can be used to study charge transfer complex. About our experiment design, we use quarter wave plate, linear polarizer, concave and convex lens, monochromator with CCD camera connected with computer, and a curved with L-cysteine solution as our instrument and the materials. Just like the equation shows here, to obtain the data of absorbance, we need I0, the baseline radiation, which is the intensity received by only our molecules, and I1, which is the intensity actually passed through our molecules. So we measure the intensity I0 with water and gravity, but no any compound inside. And we measure I1 with all the sample include water and gravity. By 5 groups data for each of LHC and RHC.
So this is our setup. We have our lamp, our beam expander with our 2 lenses, an iris to help limit the light going through. We have here a linearly polarizer. This is our quarter wave plate. This is our L-cysteine, another iris, our monochromator, and our CCD camera. From our experiment, we also used a photodiode and another linear polarizer to configure circularly polarized light using intensity. From there, once we had that, we calibrated the monochromator using a mercury-argon lamp. And then from there, we calibrate the data for intensity distribution. As mentioned in the video, we used a mercury-argon lamp to calibrate our system. The lamp provides accurate gas emission lines which can be utilized to verify and calibrate spectrometry wavelengths. These 4 peaks of our graph were indicators that we have successfully calibrated our monochromator and can produce accurate data.
First, we use the data of baseline and the intensity of light to calculate absorbance for LHC and RHC respectively. The equations are shown in this page. Then we take difference of absorbance by using absorbance of LHC minus 1 of RHC. Because CD measures differential molar absorptivity, so we have to divide the absorbance difference by molar concentration and pathway length. Here is our spectra. The plots are averaged intensity distribution of the 5 groups original data we collected. Here is our CD spectra after process the average intensity distribution as we mentioned above. For easily understanding the difference we discussed below refers to absolute value of the difference in absorbance. Through analysis of the CD image, our findings are as below. Between 363 and 535, which is violet to green, the absorbance of L-cysteine for RHC is greater. And this difference is maximum at 430 and 495 nanometer. However, between 445 and 462, which is blue, the absorbance of them are more similar. Between 535 and 600, which is green to orange, the absorbance of L-cysteine is greater for LHC, and this difference is max at 565 nanometer. Moreover, our plot agrees with the theoretical one to a great extent. The location and the size of some peaks differ. Between 350 to 400, our images are relatively smoother, while the theoretical one have 2 small local minimums. Otherwise, the shapes of the curve are largely the same for the other regions, and the error that caused this difference will be explained later. The spatial ranges and the spatial points we mentioned above are listed here.
In this report, we present CD observations and analysis of a specific chiral molecule, L-cysteine. Through the analysis of the CD images, overall the CD of L-cysteine is negative, which indicates that overall the absorption of L-cysteine for RHC is greater than that of LHC. We also recognize that the property of chiral molecule with circularly polarized light is due to the special structure of chiral molecule compounds, and that we must have had some sources of error because our results were not exactly what previous scholars have conducted. Such sources of error are the possibility of not having a high enough concentrated solution. Potentially, part of the light is absorbed by dust in the monochromator or the connection with the CCD camera that occurred after calibration, and just normal noise interference with our environment. We would also be able to have a better understanding if we used D-cysteine and compared those plots with L-cysteine. Still, the study can provide a data reference for other scholars entering this field of CD spectroscopy. We want to thank you, and we hope you enjoyed our presentation.